Hi guys, my name is Medina Aghatalibova. Today we'll consider with you the topic about the complex numbers. First of all, let's just define what means the complex numbers. Actually, we have the real numbers, which we use for the counting in the real life. So what we'll do with the complex ones? They helps us to solve such equation or expression which are actually undefined. For example, if I will take that I have the square root of negative 36, generally math tells us that this expression is undefined, but actually in terms of the complex numbers, I may get till the answer. So this will be the square root of 36 times the square root of negative 1. So 6 times the square root of negative 1. Square root of negative 1, I know that this is the imaginary part of a number. I may denote it as I. So I equals to the square root of negative 1. From here I may find the I squared, which is the square root of negative 1 squared. So just negative 1. Then if I have I cubed, just because I have the odd power, I need to express it first of all with the even one. So this will be I squared times I. So just because the I squared is negative 1, this will be negative 1 times I. And then I to the power of 4. Actually, this will be square root of negative 1 to the power of 4, so just 1. Or if I will have I to the power of 5, this will be I to the power of 4 times I. Just because the I to the power of 4 is 1, it will be just I. So from here I may make a conclusion that if I have I to the power of 4n, so the power is a multiple of 4, I will have the value of 1. If I have I to the power of 4n minus 2, this will give me negative 1 because the power is not divisible by 4. And moreover, here I want to consider the case when I will have I or negative I. If I have I to the power of k, let's tell that this k is an odd power. So I may tell that here I may have two answers negative I or I. I will have I in case when I just express it with the even power, and this even power is divisible by 4. For example, I to the power of 9. I may write that this is I to the power of 8 times I. Just because I to the power of 8 will give me 1 because it's divisible by 4, I will obtain that I to the power of 9 will be just I. If I will have I to the power of 7, I may express it as I to the power of 6 times I. Just because this I to the power of 6, so this power is not divisible by 4, it will give me negative 1. And finally, I will get the answer negative I. Now let's solve the example related to this topic. For example, I have I squared plus I cubed plus I to the power of 4 and then plus I to the power of 5. First of all, I know that I have here I squared, which is every time negative 1. Let's express what will be the value of the I cubed. This will be I squared times I, so negative I. And then I know that the I to the power of 4, just because the power is divisible by 4, will give me just 1. Now let's find the I to the power of 5. I may express it as I to the power of 4 times I, so just I. Just because this I to the power of 4 will be 1, I got the answer of 1, of I, sorry. So let's just substitute them. Negative 1 plus minus I, then plus 1 plus I. I will get that this will be negative 1 minus I, then plus 1 and plus I, so finally just 0. Now let's consider the complex number in the coordinate plane. Actually, we have here usually for the xy plane, so here should be y, here should be x. But when we consider the complex number, instead of the y-axis, we'll have the axis of the imaginary numbers, and instead of the x-axis, we'll have the axis of the real numbers. Here, the number a, so the part of the z, a, is related to the real part of a number, and the part of b, it's actually imaginary part of a number. And the length of this leg equals to the r, which is the absolute value of z, and moreover I may tell that this r is a square root of a squared plus b squared. In complex numbers we have the rule about the conjugate. Like if we have the conjugate for the complex number, so here any z with the line upward, this will be every time a minus bi. That means that for the real numbers it will have the same coordinate, but for the imaginary part it will be with the negative sign. And this leg here also equals to the absolute value of a z with the line upward, so to the r I may tell, and this r is also the square root of a squared plus b squared. Now let's consider the imaginary part, so total imaginary part at this coordinate plane. So that means that the real part equals to the 0 and z equals to the bi. So 2 points at the axis of the imaginary numbers. If I have like completely real number, that means that the imaginary part equals to the 0, and moreover I have a point at the axis of the real number, so z equals to the a. And if I have completely number 0, that means that the real and imaginary part equals to the 0 and z equals to the 0, so the point at the intersection of these two axes. So now let's consider the examples. For example, I have here 4 plus I over 2 minus I. Now I need to find the a plus b. First of all, I need to rationalize the denominator. In order to rationalize it, I need to multiply and divide at the same time by the conjugate of this complex number. So by 2 plus I. I will get that this will be 4 plus I times 2 plus I divided. Let's just notice that we have here the formula a squared minus b squared if we will multiply these two brackets. So that means that I will obtain 2 squared minus I squared. From here, it will give me 8 plus 4i, then plus 2i plus I squared divided by 4 minus 1, because like I squared is minus 1. Finally, I will get that this will be 8 plus 6i. Instead of I squared, I may substitute negative 1 over just 5. So 7 plus 6i over 5. Let's just divide them separately. It will give me 7 over 5 plus 6 over 5i. Now they want me to find a plus b. Actually, first I need to define that 7 over 5 is a real part of a number, and 6 over 5 is an imaginary part. And now let's sum them. 7 over 5 plus 6 over 5 equals to the 13 over 5, or just 2.6. Now let's consider the case when we have the quadratic function, like the quadratic equation here actually, where we need to find the x2 if they will give me that x1 equals to the 1 minus the square root of 5 times I. I will prove one theorem, but then I will explain you that there exists the term where we have like where it says that if we have one complex number, so one root as a complex number, 1 minus the square root of 5i, that means that the second root, so x2, will be just 1 plus the square root of 5 times I. So the term about the conjugate roots. But let's prove them. So by means of the Viet theorem, I may tell that x1 times x2 equals to the 6. Okay, and moreover I know that x1 plus x2 equals to the negative k, and they want to find the k. So let's prove this term. I may substitute instead of x1, 1 minus square root of 5 times I, and then multiply it by x2 until that this will be equal to the 6. Now x2 will be equal to the 6 over 1 minus the square root of 5 times I. Let's get rid of the irrationality of the denominator. So multiplied by 1 plus the square root of 5 times I and divided by the same conjugate. So finally I will obtain that here in denominator I have a squared minus b squared. Here in numerator I will have like 6 times 1 plus the square root of 5 times I divided by I squared minus the square root of 5 times I squared. Finally, it will give me 6 times 1 plus the square root of 5 times I divided by 1 minus 5. So 6 times 1 plus the square root of 5I divided by 6. I may just simplify the 6 with this one. I will get that the answer will be 1 plus the square root of 5 times I. So the x2 equals to this number. Actually, I said that it will be so by the term, by the rule of the conjugate root. So for now, let's find the negative. So let's find the k. But first of all, let's find the negative one. So it will be 1 minus the square root of 5 times I plus 1 plus the square root of 5 times I, which equals to the negative k. It's clear for me that these two ones will cancel, so 2 equals to the negative k. From here I may tell that the k will be equal to the negative 2. There is the answer. So thank you for watching for today. That's it. Bye.